Friends, we're going to discuss Kelly's paper and some counterintuitive results. Very counterintuitive. In other words, if someone offers you a bet, you have 70% probability of making $1 and 30% probability of losing $1. Should you take it? Well, no. In many cases, you should not take it. Not because you're risk averse. Simply, you should not take it because it's not a good strategy. And we're going to see how. This answers, of course, some of the behavioral finance nonsense that you hear, because they view things as one period model, not as a multi-period model. For example, your grandmother does not analyze the notion of smoking as a single event where you smoke a cigarette, but rather an activity of smoking. So risk-taking is an activity, not a single event. So once you put dynamics, as I've explained, it's kind of the game. A lot of the results in behavioral finance become nonsense, total nonsense. So let's see. So I start with I modified the proof in Kelly using the right limits, but let's say you start with, you have Vn is the value of the portfolio, or your total wealth at period n is going to be V0 1 plus R to the nth power, which is discrete compounding approach. So based on that, there exists an optimal combination, an optimal point. I'm going to see it here. It's a red dot. An optimal L. L is how much of your total capital you invest. So you invest, L of 1 means 100%. L of 0, nothing. L of 0.5 is 1/2. So there exists an optimal L that has been derived by Kelly. Again, I have a different approach, slightly different, just to make it consistent with probability limits. And as you notice, something quite strange is that your long-term return 1 plus R is going to be pretty much the same as the Shannon entropy. Why? Simply because the whole idea of Shannon entropy is based on how much noise you should have in your channel, and there exists a sweet spot, and it's the same sweet spot with Kelly. Too much noise and the message will not go through, too little noise and it's not optimal. So it's the same thing here. So let's look at the results here, and in one line of computer code will illustrate it. The blue line here is a probability of 0 of losing. Okay. The second one here is the yellowish line is 0.05, 0.1, 20% of losing here. And of course, 0.3 is the one we're going to focus on, 30% probability of losing. Now, what people found very counterintuitive in the story is that even if you have the odds, and if you invest below a certain level, guess what? You're going to go bust. Say you invest 80% of your assets at all times into something that has a 30% probability of losing, 70% probability of winning, and symmetric. You can, of course, keep the probabilities constant and change the payoff, or you can change both, but let's simplify. Symmetric payoff, you get L, you get minus L, and of course, how much you invest, of course, and then the probabilities are not symmetric. So 30%, let's say that you invest at 80%, guess what? You're going to go bust. Why will you go bust? Because there will be a few times when you're going to lose everything. So the idea of long-term strategy, and that's Kelly's idea, is that there's a sweet spot. Now you see 2 points here. Where you cross the line is where your return go negative, and you see it happens at high odds. Okay, these odds are between 0 and 50. So, and where you're certain to go negative if you allocate at that level, eventually in the long run. And the red spot is your sweet spot where you maximize your long-term rate of return. And of course, these two are important, but the most important one is avoiding bankruptcy. Let's take K0 equals 0. I have a simple algorithm, KT equals KT minus 1, where you take your capital plus some risk, where you lose L proportion of KT minus 1, or win L proportion of KT minus 1. So let's say that you allocate at 0.3. I allocate at 0.3. There you go. You have T100. You have a 7% rate of return. Whatever you have is stochastic, because we do 4 runs for each. Okay, so if you allocate at 0.3, okay, you see it's stochastic, but nevertheless they're positive. T100 after 100 periods. If you do 10,000 periods, it will take some time. You get about 7.8. Now let's say you invest at 0.8, which is we saw here. 0.8, you should be losing money. Look. Okay, 2 survived, 2 didn't survive because it's short. We go 100,000. You're bust. Eventually bust. Okay? So, as you can see, right, from here, okay, the edge doesn't matter. There's a combination of how much you bet, which, of course, is a function of how many times you're going to repeat the bet, and a lot of other things. So this Kelly thing is trivial, as you can see it now. Particularly, this graph makes things clear. But think about it. This destroys tens of thousands of papers in risk aversion, in the risk aversion literature, that evaluate things as one period model, not continuous models. So since I wrote dynamic hedging, I have been fighting with people over Ruin. Oh no, Ruin does not allow cost-benefit analysis. There's no cost-benefit analysis here. Or if you're going to do it, you have to do it over time. So my friend Ole Peters had, of course, has been fighting, of course, he and I have been fighting with Richard Taylor, who calls it something, NNT hogwash, can explain why people turn down 50-50 bet, win 110, lose $100, pure loss aversion. Richard Taylor doesn't get multi-period models. Pretty much all his work is BS. If you put more richer structure, or if you put more probabilistic rigor on it. And of course, Ole Peters is very rigorous and has done a great job promoting something he called ergodicity economics, where we look at things over time, multi-period models, not simply one-period model. Thank you for listening to me, and have a great day. Bye now.